Our first section is just about waves and energy transfer. We're doing things like basic definitions and looking at what exactly a wave is. So, as we know, communication is very, very, very important to us human beings. The fact that it was developed a few thousand years ago made it possible to communicate ideas and made it possible to come up with more complex ideas. And with those complex ideas, they could be implemented in the real world thanks to the communication between the people. And so it used to be that if you wanted to send a message a very long distance, it would take a long time. You would have to give it to a messenger and they would take the message and go over to the recipient and deliver it. These days, we don't really need to wait so long for communication. Today, we use electromagnetic waves in order to communicate with each other. And so these waves travel so quickly that you don't even notice the delay for the travel time. It means that if we use a mobile phone, we can speak with someone on the other side of the world and notice hardly any delay in the message's travel. Waves are also responsible for other forms of communication. The main one that we'll be looking at in the module is electromagnetic communication, but the other waves are quite important as well. So I've mentioned waves quite a lot now, so we should probably get on to defining them. There are many different kinds of waves. There are obvious waves, like as we can see in this picture here, waves in water, which you've probably heard of. And as it turns out, light is a form of wave as well. And that one's not immediately obvious. So right away we can see that there is more than one different sort of wave, and they have different properties. So given they're so different, how can we find a definition that covers all different types of wave? Well, it turns out that all waves, regardless of what sort of wave they are ways of transferring energy without transferring matter. So we're getting energy across, which might be a message or some sort of energy pulse, and we're not having to move any objects to transfer that energy. So if we look at a water wave, for example, we look at it passing across a few things floating on top, we'll notice that most of the time, the things on top don't actually move in the same direction as the wave. They just bob up and down as the wave goes underneath. If a wave is breaking, as a surfer might catch, then it will be a little different. But if we look at objects floating on top of the water, like these ducks, we can see that they'll move up and down. They'll bob on top of the water as the wave goes past, instead of being carried off by the wave. And so the water wave is not causing the water particles to move in the same direction as the wave. It is simply causing them to move up and down as the wave passes. Let's look at another example. If we look at a piece of string or a rope tied to a wall, then we can sort of flick one end to make a pulse travel down the string. So shaking the string at one end will cause the string at the other end to also shake in the same direction. And in this case, it's obvious that the string isn't moving back or forth, right? If we send a pulse down, then we don't have to get the entire string moving in that direction to carry the pulse. All we need is that little disturbance in the string to propagate through the string. So in this case, we're once again transferring energy without transferring matter. If we look at light, this is a type of wave that travels through physical space, right? It doesn't have water or string to travel through. If you could take hold of a little charged particle, for example an electron, at one end of the room and wiggle it around a lot, then you would create electromagnetic waves. This means that if you were to look at a similar charged particle on the opposite side of the room, it would behave in the same way as the particle that you originally jiggled. It's as if you were holding a string at one end of the room and shaking it up and down. It causes the other end of the string to also shake up and down. Except instead of ropes propagating through the wave, propagating through the string rather, they're propagating through empty space. So electromagnetic waves turn out to be the fastest type of wave. There is no wave that goes more quickly than the wave between two charged particles jiggling. So it turns out that, as we know, we can change some forms of energy into other forms of energy. And this is true for the energy carried by waves as well. So why is this important? Well, modern communications often use electrical energy, right? We have lots of electrical appliances, like mobile phones and satellite communication and instant messaging. And these all need to use electrical energy in order to carry messages. So if we can transform things to and from electrical energy, that means that we can use electrical waves to transmit messages. So we can, once it's being transmitted as electrical energy, we can transform that back to a form of energy that we can understand, like sound energy, if we're talking over a telephone. So let's take a look at the various energy transformations that happen when we talk on a mobile phone. We start off with sound energy when we're talking into the mobile phone, and the mobile phone will very quickly use its microphone to transform this into electrical energy. With me so far? Okay, now we take this electrical energy and we transform it into an electromagnetic wave. The type of electromagnetic wave is called a radio wave. And so once it's a radio wave, we can actually beam that to a mobile phone tower, and that'll send it up to a satellite in the same form. The satellite will decode part of this and then send it back down, still as a radio wave, into the destination mobile phone, right? And that'll transform it back into electrical energy once it's inside the phone. Of course, we can't hear electrical energy. What we need is a speaker on the receiving phone in order to transform the electrical energy into, that's right, sound energy. And once it's back in the form of sound energy, the recipient can receive the message that the sender sent. So in this case, we have a number of different transformations of energy just to transmit a single message. But because one of the transformations turns it into radio waves, we can transmit that message extremely fast and extremely long distances. So it turns out that all types of non-electromagnetic wave require particles interacting with each other in order for them to propagate. So if we have particles, then all those particles acting together must form some sort of substance. So the particles might be molecules or atoms or something, but whatever they are, they're making up something bigger. And we call that bigger thing the medium. If we think of sound waves traveling through air, then air is the medium. It's the particles in the air that let the sound wave travel. So some media, which is of course the plural of medium, that we see carrying waves might be the air, or water, or even a string, if we're doing a science experiment to demonstrate waves. Or if we're playing a musical instrument, for that matter. Now, when an object vibrates in a medium, it causes a disturbance. We can see that in this series of diagrams over here. A cork has been dropped into some water and caused a disturbance in the water, right? Now, that disturbance will actually travel away from the object. We can see that the vibrations caused by this cork are spreading outwards. As they do this, they're taking energy from the cork's vibration and carrying it away from the cork. And that means that we have energy being transferred without matter being transferred, hence a wave. So if we look at, once again, our example of a falling cork, it will produce ripples in the water. So these ripples are a form of wave. If we look at the water in the ripple itself, if we could look at the atomic scale and look at the water molecules, we would notice them only moving up and down as the ripple passed, without actually moving in the same direction as the ripple. Now, most waves turn out to arise from vibrations. So, as particles in the medium vibrate, they cause the particle next to them vibrate. So, once again, an easy way to look at this would be a string. If we see one part of the string start moving up, then it will pull the next part of the string up with it. As it moves back down, the next part of the string will move back down as well. So as the vibration spreads out, the wave propagates through the medium. Propagation is what we call it when waves are traveling through a medium or through empty space. Now, waves can occur in different numbers of dimensions. Right? We can look at waves in one dimension, which are the easiest to examine. We can look at waves in 2 dimensions, or even in 3 dimensions. And all of these waves will look a bit different. A wave in 1 dimension might be a wave on a string, for example, in a violin. A wave in 2 dimensions might be ripples on a pond. We can see that they don't just spread out in one direction, they spread out all across the surface of the pond. So that means that they form a circle away from the original disturbance. So if a 2-dimensional wave looks like a circle, then what might a 3-dimensional wave look like? Well, you've guessed it, a sphere. So if we look at something emitting sound or light, like the sun, the light will spread out in 3 different directions. Make sense? Sound works as well. If something makes a noise, then no matter where we're standing around it, we'll hear that noise. So that means that the wave is spreading out in all different directions. And so it's a 3-dimensional wave. All right, so now that we've got some idea of what waves are and what some different sort of waves might look like, let's go on to some questions.